we would like to thank and acknowledge our sponsors, Boyce Astro and Chroma Technology. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving both the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation and surgical devices, machine vision, multispectral imaging, and of course, everyone's favorite, astronomy. Their website is also up there on the screen if you'd like to check them out. All right. Today's instructor almost needs no introduction. The current secretary of the AAVSO, she's been active in the organization for years and has also served as both a council member and AAVSO's president in the past. She's also an astronomy professor at Central Connecticut State University, where her research focuses on the intersections between science and society. She's written several science books and received a number of awards, including the Walter Scott Houston Award of the Northeast region of the Astronomical League. And of course, she's also the leader of the AAVSO's Solar Observing section. Last November, she presented us with a very popular webinar all about how to get started observing the sun safely. Today, she's back to share with us a follow-up all about sunspots and the unexpectedly interesting topic of how to count them. It's a timely topic indeed as we head into solar maximum, with plenty of sunspots already erupting on the surface of the sun while it wakes up from its dormancy. Personally, I can't wait to learn more. So it is with great enthusiasm that I present to you your instructor for today, Professor Kristine Larsen. Welcome, Professor Larsen.
Thank you, Lauren. Thank you very much. And I would like to say that in the audience, we have one of the primary authors of the AAVSO Solar Observing Guide. Frank Dempsey is with us today. So there is definitely a huge brain trust of safe solar observers here today to answer all of your questions. So while I bring up my PowerPoint, all right. So I can't resist having a little bit of pop culture in any of my talks. Those of you who know me know this. And so today we're going to have our seminar brought to you by the letter S for sunspot and the number 11. And the reason why the number 11 will become apparent very quickly. So here is the obligatory disclaimer. Please do not look at the sun unless you know how to do it safely. For example, by consulting the AAVSO Solar Observing Manual, and that you, in the end, are responsible for your own safety when viewing the sun. In case you don't know, the sun is a lot bigger than the Earth. I love showing this picture to my students because you can literally see their jaws drop. The little tiny dot over here represents the Earth. We are not that close to the sun, but if we were that close to the sun, we would be in trouble indeed, because solar activity absolutely swamps, literally, the sides of our planet. The kind of observing that we're going to be talking about today is what we call white light observing. We're going to be observing the sun in visible wavelengths, what our sun would see. We're going to be talking about looking through the telescope or looking at a projected image of the telescope and counting the number of sunspots and monitoring solar activity. Now, people will sometimes ask, well, why don't you just count the number of dots you see on a photograph? And the reason for that is that those of you who know the AAVSO know that the main reason why our data is so valuable is because of its long, consistent history. We have been observing the same objects for a very long period of time, using the same methods and using similar technology. And it's like comparing apples to apples. Comparing visual observations of the sun from 100 or 150 years ago to CCD pictures today is not comparing apples to apples. So that is why we're going to be talking about the person safely, visually looking at an image of the sun and measuring what they see. And so the layer of the sun that we are going to be viewing is what's called the photosphere, the visible surface of the sun. Surface with scary air quotes because it obviously is not a solid surface. You don't stand on it, but it is the top dense gaseous layer that is opaque, that we can't see through. And what this layer actually represents is the top of what we call the convection or convective area of the sun. It is literally boiling. So with high enough resolution, you can actually see these convective cells on the surface of the sun, and we call this granulation. And as you know, hot gas rises and cooler gas sinks, and this allows us to have hotter, brighter regions and cooler, dimmer regions. There are areas that are even more intense in their temperature contrast. We have areas that appear darker than average, and those are the sunspots. In text from like the 19th century, you'll sometimes see the term maculae, and that is in contrast to what we still today call faculae, not faculty. Not all faculty are bright, but all faculae are bright. So faculae are brighter appearing regions on the photosphere, and because they are brighter, they're easier to see when there's a contrast. And so as we're going to see, no pun intended, faculae in particular are easiest to see when they're on the edge or limb of the sun, as opposed to sunspots that are easier to see when they're sort of in the middle of the sun. And the reason why faculae are easier to see when they're on the limb of the sun is something called limb darkening. So what is limb darkening? The photosphere, this layer of the sun, even though we think of it like as a surface, it's actually a layer. And there's a temperature gradient that the top is cooler than the bottom. And so when you're looking through the edge or the limb of the sun, you are looking through more of that cooler gas. And so it appears darker. And therefore there's more contrast with the overlying bright faculae that sort of look like bright threads. If you're looking towards the center of the sun, you are looking through less of a shorter or smaller layer of that cooler gas and seeing into the brighter part beneath. And so therefore there's not as much contrast. Now, sunspots are the most obvious of all solar activity. They appear dark not because they're black, but because they just emit less light than the surrounding photosphere because they are about 1500 degrees Kelvin cooler. If you could surgically cut out a sunspot and hold it with some asbestos tweezers so you don't burn yourself, it would actually glow like the dying ember of a fireplace or a campfire. It would be sort of a dull magenta color. Now, sunspots are always changing and growing. They can last for hours. They can last for weeks. There are some sunspot groups that have lasted for about 2 months. And the reason why we monitor sunspots is not because the sunspots themselves directly affect the Earth, but because other kinds of solar activity that more directly affect the Earth are related, are born from, are spawned from large sunspot groups. So these are a reasonable, very easy to observe safely proxy for other kinds of solar activity. If you look in detail at very large sunspots, you will see that there can actually be structure within a sunspot. Just like the terms that we use for the inner and outer part of the shadow in an eclipse, the inner, darker appearing part of a large sunspot is called the umbra, and the not quite so dark outer part is called the penumbra. Now, here is one of the interesting quirks about monitoring sunspot activity. If you have an isolated sunspot by itself in the middle of nowhere on the sun, we call it a group. We call it a spot. but we also call it a group. What you need to think of is a group of sunspots is representing an active area on the sun. It doesn't matter how many spots are part of that active area, but the fact that that is an active area is very important. It might spawn solar flares or coronal mass ejections. The point is that an active area on the sun is worthy of making note of, regardless of how many individual spots belong to that group. So here you can see on this picture, you have a lot of what look like isolated spots that have an active region number associated with them. They are indeed single spots, but they are also considered a group. When you look at groups or active areas of the sun, you will often, but not always, see what we call a buddy system, a bipolar activity here. The way I normally will discuss this with my students is think of a horseshoe magnet. A horseshoe magnet is shaped like a U. It has a north and south magnetic pole, right? Well, imagine dipping the feet, the poles of the horseshoe magnet in ink, and then putting them on the sun. And what would you see? You would see two spots. And indeed, in one of these bipolar groups, one of those spots has a north magnetic polarity, and the other will have a south magnetic polarity. And so why do sunspot groups commonly occur in bipolar groups? Because of their anatomy, because of their physiology. A sunspot group is a place where the magnetic field lines of the sun poke through the photosphere, curl around, and come back down. And this actually curbs or suppresses the convection. It suppresses that natural rising of hot gas. And because of that, the area around where the magnetic field line pops up, the sunspot itself, is cooler than average and will appear darker. Now, something that was noted by Galileo, and again, other people, not just Galileo, observed sunspots in the 1600s and before. We have records going back thousands of years of people seeing sunspots with the unaided eye. But one of the early observations that Galileo and others did when they looked at sunspots with those first telescopes was that not only did the individual sunspots change from day to day, but the relative position on the sun changed as well. And this was the first evidence that the sun was rotating. And the interesting thing about the sun is, first of all, it rotates relatively slow. It takes about a month to spin once. But also, the sun does not spin as a solid block. It doesn't spin as a ball because it's made out of gas, convecting gas. So what happens is that sunspots at the equator move faster than the sunspots at the pole. And we call this differential rotation. And the net effect of this is to twist up the sun's magnetic field. I usually use the analogy of cats playing with a ball of yarn. And if you have a cat playing with a ball of yarn, it gets tangled up, and eventually you get frustrated and you probably just cut out the bad part, throw it away, and tie it back together again. Well, that's pretty much what the sun does every 11 years. And so the result is what we call the sunspot cycle, the changing number of sunspots, the changing measure of solar activity over a roughly, very roughly 11-year period. The time from peak to peak can be 7 years, it can be 17 years. On average, it's about 11 to 11.3 years. So if you look at this picture of some of the recent sunspot active periods, the solar maximum, you'll notice that not every maximum is created equal. Some cycles are more active than other cycles. This is part of the joy of the sun. You don't quite know what you're going to get. You can only guess. Now, the sun is therefore considered a variable star. It is a rotational variable because as it rotates, we see different spots and see different activity. It is more specifically a spotted rotating variable. It has two periods, one of about a month due to the rotation, and one of about 11 years due to the sunspot cycle. Now, again, I talked about the kittens and the yarn and just cutting out the bad tangled up yarn and throwing it away. And I said the sun does something similar. That phenomenon is what we call coronal mass ejections, huge bubbles of gas threaded with magnetic field lines ejected from the sun. And so if you've heard people talk about, oh, those darn solar flares, they're messing with everything. It's not necessarily the solar flares. The coronal mass ejections are really responsible for a lot of what we consider to be sunspot related activity affecting the Earth. Essentially what happens is that solar activity can interact with the magnetic field of the Earth, and this geomagnetic activity can create all sorts of really interesting, sometimes beautiful, sometimes very annoying, and sometimes dangerous activity. The most beautiful, of course, is the aurora, the northern lights. But it can also cause power outages. It can also disrupt radio communications. It can pose a radiation danger to astronauts, and it can decay the orbits of satellites and fry their electronics. So it would be nice if we could predict solar activity, but it's a little bit better than using a magic 8-ball, but in some ways not that much off. At the bottom right here, this red line was the official forecast of the current sunspot cycle, solar cycle 25. The actual data is in black and the smooth statistical average is in purple. And you can see that since the minimum in 2020, the sun has been outperforming the prediction vastly. Like I said, it's a little bit better than a magic 8-ball, but only a little bit better. So this is why we want to measure and observe solar activity. We want to improve our models of the sun so that hopefully we can get to a point where we can better predict solar activity into the future. So the way that we observe and count sunspots goes back to this gentleman, Rudolf Wolf, from the Zurich Observatory in the mid-1800s. And he would observe the sun every clear day using the same technique and using the same instrumentation. And he is responsible for coming up with the system of measuring and delineating solar activity. And so it's based on two things: the total number of spots and the number of groups. Now remember, I told you that a group is an active area. It is an area of the photosphere that is independently active as compared to other areas on the photosphere. So a group could also be, remember, a single spot. So the so-called Wolf number, sometimes it's called the Zurich number, you take the number of spots, you count them all up. You take the number of groups, you count them all up. But the number of active areas is more important than the individual number of spots. So we're going to give it a statistical weight. So we're going to take the number of groups and we're going to multiply it by 10 to give it an order of magnitude more significance. So the Wolf number is 10 times the number of groups plus the number of spots. So for example, in this picture here, there are 6 groups. 1, 2, 3, 4, 5, 6. So you take 10 times 6, that's 60. If you count up all the individual spots and all of the groups, you end up with 53. 53 plus 60 is 113. So the Wolf number or Zurich number for that day would be 113. So here's the really interesting thing about counting sunspots. It goes from 0 and then 11, 1 louder, Spinal Tap. There's nothing in between. Because remember, if you have if the sun just has one spot, like on that picture, one spot, that is also a group. So it is 10 times 1 is 10, plus 1 is 11. So if there were no spots the day before, it would be 0. And then the next day there's 1 spot, it jumps to 11. So there's nothing in between. So that's why today's lesson is brought to you by the number 11. Now, this was all well and good when Wolf was the one doing it because he was a standard observer. We were comparing apples to apples. But what do we do to compare other observers afterwards? And what if, and now we take groups, we aggregate. There's about 70 people who are observing the sun for the AAVSO. How do we compare those different apples, the different kinds of apples, and try to keep a nice, consistent, historically relevant data set? What they began doing after Wolf was talking about something called the Zurich reduction coefficient, the relative sunspot number. What you do is you take the observers and you say to yourself, this is what they were observing. How does that match up with, let's say, what Wolf would have observed? What is the multiplicative coefficient that would bring those two into alignment? And so what we do is we multiply the 10G plus S times what we call this K factor. And the K factor is that normalization, if you will, that brings everything up. So every observer has their own K factor. Now, don't worry, you don't have to calculate this. The AAVSO has long-standing statistical programs that are reviewed from time to time that will actually do that for you. But just so you know that there is some statistical work that is done to try to make sure that we keep the apples to apples so that we can go back and compare historically the data in the database. Another interesting thing about observing sunspots is that you don't find them normally near the north and south magnetic pole or the north and south geographic pole. You tend to find them within about 45 degrees north and 45 degrees south, but normally not on the equator itself. And within a group, the sunspots are arranged very roughly parallel to the equator. So you can see here that in this group over here, this large group that has 27 spots, you can see here that they are kind of in a straight line, but the equator goes right across the middle of this picture. So you'll notice that they're not quite aligned with parallel. It looks like this spot over here, the leading spot, is a little bit closer to the equator than the spot trailing behind. And that's called Joy's law, that within a group, the spots are tilted a little bit, not exactly parallel, but they're tilted by a few degrees. And this is information that can be useful when you're trying to figure out where the various groups are on the sun, especially when the sun gets really, really crowded, as we'll see. Now, the north and south hemispheres of the sun are related to each other, but the magnetic fields can kind of do their own thing to some extent. So what we want to do is we want to actually not only look at the number of, the number of spots and number of groups, but if we can, we want to figure out how many of those are in the northern hemisphere of the sun and how many are in the southern hemisphere of the sun. In this picture, you can see that in red, we have the sunspot activity of the southern hemisphere, and the N is the north, and you can see that it's different. So we want to monitor this. So you need to figure out where the equator is on the sun. Now, again, if you use Joy's law and the fact that they think that they're roughly, the spots within a group are roughly parallel, that can help. But where the equator is on your view is going to change. It's going to change depending upon where the sun is in the sky, what angle you're holding your head, if you have a diagonal and you're looking through at some weird angle. And it also depends on the time of year, because let's face it, everything is tilted, right? The Earth is tilted with respect to the ecliptic and it's tilted, right? So this is a nice diagram that shows you, roughly speaking, over the course of the year, where the equator of the sun will appear to be in your field of view, how it will seasonally change. Also remember that your view through your particular telescope can be inverted, right? Things can look upside down. So if you are interested in figuring out the difference between the northern and southern hemispheres of the sun, you need to be able to identify them in your telescope. So this is how I normally explain it. I actually have done this with like a hula hoop and a pie plate so my students can see it. If you think about the field of view of your telescope, okay, so the field of view of your telescope is this reddish circle, and there's the sun centered in the middle of your field of view. Now let's imagine that you push down the nose of the aperture of your telescope, so your telescope is pointing more south. If your telescope is pointing more south, the northern part of the sun is going to disappear first. So let's say that I physically push the nose of the telescope south, and this part of the sun disappears first. Well, that must be the northern part of the sun. Okay? Now, this is easy to do if you have an equatorial mount. You just move the sorry, that should have said declination, not latitude. You move your declination knob, and with your Dobsonian, if you're observing near noon, you would just move it down in altitude. So again, if you want more information on observing the sun, I'm going to point you to the AAVSO website and the solar section. Rodney Howe and I are the section leaders, and Kim Hay she is responsible for putting together the monthly bulletin and is an absolutely wonderful human being and will answer any questions. And Sarah Beck is our point person in headquarters, and she's also very good at answering questions. And again, our observing guide, which is available in different translations. And very quickly, just to remind you that there are 2 different ways that you can solar observe. We currently have about 70 observers, about half use projection and half use filter. The projection method, you are projecting the image onto a screen. There are pluses and minuses to doing the projection method, and I will point you to the other webinar that Lauren had talked about if you want to learn more information about safely observing the sun. Filter prevents the light from entering in the first place, but you have to make sure that your filter is in good working order every time you use it. And you're not going to use your finder scope to find the sun. You're going to line up the shadow. So once you have observed the sun, you're going to submit your observations through the sun entry program by logging in using your AAVSO username. And you can see that there is a place where you pop in your group number for any given day, your spot number. It automatically will give you the wolf number. If you want, you can put in the number of northern groups and northern spots and southern spots. And you can also put in what we call the central zone. The central zone is the central half radius of the sun. Think of this as the sunspots that are sort of pointing straight at us. You can see how, if there's activity associated with that, that might be important. And again, the northern, southern, and central is optional. You don't have to do that. Just reporting the total number of groups and the total number of spots is perfectly good. And the great thing is that your data lives forever in the database. You can find your observations and find how many you have. I currently have 1,273 that are in the database, and I have a couple of hundred from before we did this database, which are fortunately not in there and not counted towards my total. So I'm past my 1,000 and on my way to my 1,500. And the monthly solar bulletin, you can see how the sun is doing, and you can compare your observations with those of others. So here is a page from, this is the June number. The July numbers haven't been printed yet, they're in press. So for June, you can see that on any given day, there were differing numbers of observers depending upon the weather and life circumstances. You can see the raw numbers, and then you can see the numbers with all the K factors put in, okay? So RA, the American relative sunspot number, that would be the wolf number, the number essentially calculated by the AAVSO with all the K factors in it. Now, there are some subtleties to counting sunspots. You will see things depending upon how, how good your observing is that day and the resolution of your telescope, you may see faint things that you're like ghosts of a sunspot. What is that? Is that a really faint sunspot? These are things called pores. They are fuzzy, they have low contrast, they're not dark. Don't count them. Also, don't count any broken pieces of penumbra. Like here's a broken piece of penumbra here. You wouldn't want to count that. And don't count any really tiny spots that you have to crank up the magnification to be able to see. So, a good guideline, and this is from the Solar Handbook, observe at several powers, use low power and medium power to see the entire sun and to identify the groups. And then if you can use high power to see where the small groups are, but you don't want to count the pores. So the actual sunspots, you can see here, they're darker, more obvious, circled in red, and then these nebulous sort of pores that are circled in blue. You also want to be very careful looking along the edge or limb of the sun, because it's very easy to miss sunspots if they're right on the edge, okay? And if you want to know sort of where to kind of look for where new sunspots are coming from, if you see any area of faculae, any of those brightish threads I talked about on the edge of the sun, that's where you're going to want to look, because that's prime breeding ground for new sunspots. So remember that faculae are easiest to see along the limb of the sun because of the higher contrast, because of limb darkening. Now, your ability to count sunspots is very much dependent on your observing conditions. I like this diagram because it shows you how, depending upon what your observing conditions are, you will get a different count of sunspots, right? So here we have excellent observing, you can count 16 sunspots. If there were poor observing, poor seeing conditions that day, you would only see 6 sunspots. Right? But assuming that this is all one group, let's see how that might affect the Wolf number. There's already a factor of 10 because it's one group. If it was excellent seeing, this would give you 10 plus 16 is 26. If it was poor seeing, it would be 10 plus 6 or 16. So you have a difference between a weight of 16 or 26. Now, most of the time you're going to be in the fair to good. And so that would be a 17 to 22, which is, there's a difference between 17 and 22, but not a huge difference between 17 and 22. So you can see how weighting by a factor of 10, that area of activity helps to take into account differences in seeing conditions and also observer conditions, just the observer's eyesight. So let's see if you can figure out how many groups are there on the sun on this day. So look at this picture and I'll let you go ahead, put in the chat, how many groups do you see? How many groups do you see? Okay, I see some, right, excellent job. I see people putting in their answers. Wish I had the Jeopardy theme playing in the background. All right, so here is the answer. Those are the different areas of activity. We have 1, 2, 3, 4, 5. Isolated spots and things that are a little more interesting. All right, how many groups are there here? How many groups are there here? Go ahead and put your guess in chat. Right. 1, 2, 3, 4. Some sunspot groups are very large, take up a lot of real estate. Well, what about when the sun looks like this? This is a hot mess, as my students would call it. You definitely don't want to start solar observing at the peak of sunspot maximum. Trust me, that's when I got started and I was pulling my hair out. You definitely want to start now when the sun is a little less active and you can kind of ease into it. When the sun is a hot mess like this, how many groups are there? Wow, a lot, right? Well, I don't know the answer for that day. So I went through and I tried to figure out with my best guess what I thought the different groups were. And that was my guess. This stuff in blue, I'm not so sure about. So I just sort of put that in a different color because I'm not quite so sure about that. But yeah, I mean, yeah. I do know that on this day, the wolf number was over 200. The sun was incredibly active that day. So you get the idea of the difference between a mild-mannered, a completely blank sun, my students call Winnie the Pooh's butt, because it kind of looks like this giant round orange thing. And then it goes from 0 to 11, one louder, and then it can go to this or more. So when the sun is really active, how do you know where the new sunspot groups are popping up? Well, it's okay to monitor the sun to see what's going on the days that you can't observe. If you go to, for example, spaceweather.com, they put a picture of the daily sun. They identify different areas of activity. And so you can keep track of new groups that are rising up, so that the next time you go to observe, you're not starting from like a blank slate, and you can kind of keep track of, okay, that one group that I was looking at, it looks like it's gone. And then there's this other group that popped up, and then another group popped up over here, and I don't want to get those confused. Do not go to this website, count the dots, and submit that as your AAVSO observation. No, no. This is just to help you to kind of keep track roughly of what the sun is doing between the times that you can observe, so you're not going in completely shell-shocked when you look at the sun next time. It's also can be helpful to look at how sunspot groups can change, can evolve over time. There are different systems of classifying sunspots. The one that the AAVSO is using is the Zurich classification. This is, again, taken from our wonderful AAVSO observing guide. And this shows you all the different this is the taxonomy, the Linnaean taxonomy of sunspot groups. They can be little bipolar groups with no penumbra. They can be bipolar groups where one of the spots has a penumbra and the other one doesn't. They can be huge, messy things. They can be ginormous, messy things. And then they usually start small, they grow, and then they can what we call decay. So looking at the different sort of taxonomy of sunspot groups and being aware of the different shapes and sizes that they can have can also be very useful. But to improve as an observer, experience. This is way back, when I was first starting. I didn't know what I was doing, to be honest with you. And so I would count what I thought were groups, and I went a little group crazy sometimes, inventing groups on the sun. And so what I would do is I would go back later when the solar bulletin was published for that month, and I would compare the published number to what I had gotten. And I would undoubtedly find that my numbers were higher. And so I would go back and look at my picture, and I try to learn from it and try to figure out where I went wrong. So this is from June, because remember I said that we have the June bulletin published, but the July bulletin will be coming out in about a week. It comes out the next month. You can see that on this particular day, I nailed it. But here's one where I was very bad. I was actually very sloppy on this day, I'm ashamed to admit. The problem is that these sunspots were very near the limb of the sun. And I totally forgot about limb foreshortening, about the fact that we're looking at this as a three-dimensional object, not a two-dimensional object. And there were two different groups of sunspots coming around the corner. These were two different groups. And I should have known that, because if I looked 4 days later, two different groups. So my bad. But here I am on the 14th, and you can see that my numbers are pretty good. So the best way to become a better observer is simply to observe more. Take your time, learn from your mistakes, okay? So I thank you all for your attention, and I hope that you want to join us, the few, the proud, the spotty, the solar observers. We have our 1 star, and we love it. So thank you very much, and I'd be happy to answer your questions.
Thank you so much, Professor Larsen. That was an excellent presentation. I see we do have a number of questions already rolling in, so let's go ahead and jump right in. First question here, this one comes from Kevin Haslag, who asks, are the counts of sunspots affected by the resolution of the observer's instrument?
Definitely, that's why we try to tell our observers not to use 16-inch telescopes to observe the sun. We're looking at smaller aperture instruments. If you have larger apertures, we would like you to stop them down. Or something around 3 inches would be perfect. But, you know, and that's why we're saying don't use 200 power magnification. We're trying to compare sort of apples to apples. Again, if you are a particular observer who is using and when you fill out your data for the database, you put in information about your instrument and its aperture and whether you're using a filter or projection and what magnification you're using. And if, for example, it was found that you are always higher than everybody else because you're cranking up your magnification and you're using a ginormous telescope, that can be factored into your K factor to bring you back down to everybody else.
Thank you. That makes sense. Okay, next question. We have a couple questions here that are asking about time. So first from Neil Simmons, how precisely should we record our observing time?
I normally do mine to within 15 minutes, just to give you an idea. Obviously, we would like you to do it as, you know, we don't care to the second, obviously, but I would say within 15 minutes should be fine. Because again, you're going to be out there observing for some period of time, right? So that would be a good number. And it's obviously everything is done in UT.
Okay, thank you. Next question here comes from Joyce Guzik, also on the question of time. How does the sunspot number account for time of day around the world since the sun is constantly rotating?
Yeah, that's an interesting, again, if we measure the day by UT, we all agree on when the day starts and stops. Now, over the course, if you have a particular group right on the limb, some observers are going to see that group that day, and some observers aren't. So depending upon when in the day it rotated around, it's going to jump from, let's say that was the only group on the sun, okay? It would go from 11 to 0. So you'd have a whole bunch of observers who had 11s, and then you'd have a bunch of observers later in the day that it would have 0s. And then you would have an average based on how many observers saw it. And so that's why it's not that the day-to-day observations are as important as the trends. If you look at the solar bulletin, the daily sunspot activity is counted there. But you also see a smoothed trend, and it's the smoothed trend that's actually more important, right? So yeah, those are some of the interesting little vagaries, because someone will be like, oh yeah, what'd you get for a sunspot? Oh yeah, I got a 0. What do you mean? There was a spot over there. Oh, wasn't there when I saw it. So.
Okay, thank you. Okay, next we have a couple of questions about equipment used for viewing the sun. So first of all, we have a question from Michael Gardner who asks, are there particular good solar filters that we should use or bad ones that we should avoid?
Well, for bad ones, do not use a eyepiece filter. Back in the day, back in the 60s and 70s, there were some cheap refractors, that came with the solar eyepiece filter. No. If you're going to use filter, the filter goes on the business end of your telescope. It prevents the light from coming in the first place. So you want to use an aperture filter if you're using filters. There are debates as to how good Mylar, although I have seen some, if Frank wants to chime in with his opinion, I've seen some research that says that the Mylar filters that show a bluish image of the sun have lower resolution than the ones that show the sun in sort of this truer yellowish orange that we see with the evaporated metal on glass.
Okay.
So, but in terms of what I use personally, with my equipment, I have always used Thousand Oaks metal on glass. That's what I have personally used. And I've been solar observing since 1989, and I can still see and everything is good. So, but again, it's really important to always check out your filter every time you use it. Visually inspect it for any scratches, any dings, hold it up to the sun and look around and make sure there aren't large, bright spots. If you have tiny little pinpoints, you can fix those and mask those off. But your filter will have a lifespan depending upon how you take care of it and just its natural exposure to the air.
Good advice, thank you. So speaking of actually the different colors of Mylar filters, we had a question on that topic come in from David Ordines, who asks, do you find significant differences in sunspot count depending on the color cast of the filter?
Again, I have seen some research that suggests that the ones that have that bluish have a lower, you see fewer sunspots. I haven't seen any data recently. This was older papers that I've seen. Mm-hmm. If anyone has seen any more recent data, I'd be very interested. That might be something that Rodney and I can see if we can get some more up-to-date information and maybe put something in the bulletin. Because it sounds like there's interest in that. So
yeah, great. Okay, going back to questions about filters and how to observe safely, we had a question come in from Raymond Oltian who asked, could I use solar observing glasses, cut them apart, and tape them over my binoculars for observing?
Not if you want to see. Hate to be flippant, but they are shaped like glasses because you're supposed to wear them like glasses on your nose. They are not for use with visual aid. Now, having said that, you can buy Mylar and solar filter material. Like you can make your own solar filters for your telescope and for binoculars. And there are plenty of instructions online on how to do that. You buy the material, which has the correct density, which filters out the correct percentage of light. And we're filtering out not only visible light, but a good solar filter should also filter out some ultraviolet and some infrared. And you can attach it to things that you can stuff on the end of your binoculars. So should you use your regular solar observing eclipse glasses with a camera or with binoculars? No. Can you easily build yourself binocular solar filters? Yes.
Good answer, thank you. Okay, another question here, this one from Philip Gebhardt, who asks, can you use a pinhole device in order to effectively view sunspots? If
they are very large and if you have a large image. As I said, even though we talk about sunspot observing going back to the time of Galileo, we have records of what we call naked eye sunspot sunspot observations going back thousands of years, because very big, like that ginormous group of sunspots I showed you, and that one picture where the sun looked like it had leprosy, you can actually see those with your eclipse glasses very easily. And in past times, when people looked at the sun when it was low in the sky through clouds or through smoke, they could actually see them. And so we have ancient records of sunspot activity. And what's interesting is I've seen some papers where they have taken those sunspot observations, pre-telescopic sunspot observations, and try to see if you can see a sunspot cycle with them.
Cool.
So take that for what it's worth. But yeah, so yes, if you had a pinhole projector, it would have to be a very long focal length pinhole projector to get a large enough image, and you had a large enough sunspot group, you could do it. But on a daily basis, you probably would not see on a daily basis sunspots large enough to see. It would be the special big boys that you'd be able to see.
Okay, thank you. And one more question here on the topic of safe observing methods. So David Ordeens had asked about both the Batter solar safety film and Herschel prisms. So can you speak about either of those?
The Herschel wedges, yeah. We really don't recommend Herschel wedges. We really recommend using an aperture filter, in other words, a filter over the aperture of your telescope, or using projection. In terms of the Batter solar safety film, I have no personal experience with it. If it is rated for use in telescopes, then these people obviously don't want to get sued. So obviously, if it has a safety record, then you can use it.
Okay, thank you. And we did have a comment come in on one of the earlier questions. Jay Miller commented that Daystar makes solar filters specifically for binoculars. So those do exist out there.
Oh, I'm sure.
Okay, so Stephen Zakosi asked, do our observations have to be made in white light only, or can we also use a H-alpha telescope?
For the relative American sunspot number, which is what we are doing, comparing apples to apples, the AAVSO, to give you a little bit of history, the AAVSO observations go back to basically World War II, when it was very hard to get data from Europe. And because solar activity can affect radio communication, and radio communication is very important to the military, you can see how this was disruptive. So that was one reason why the AAVSO got involved doing the relative American sunspot number. So comparing apples to apples, we are using white light visual observation with your eyes, not a camera and not at other wavelengths. So at this time, I mean, people ask us every once in a while about hydrogen alpha, especially because now hydrogen alpha, like I have a small hydrogen alpha solar telescope here at the university, and they're great. It's not what we're using for the relative American sunspot number. Also, the hydrogen alpha filters, you're really looking at the chromosphere, and we're here looking at sunspots on the photosphere.
Okay, that makes sense. Thank you. Okay, now we did have one more question here. This one came from Facebook. Someone asked if you could tell us about vacuum pressure eye solar scopes. Letter I.
I have no idea. What's it called?
Vacuum pressure eye, and that's the letter I, solar scopes. It may be in the context of narrowband H alpha
Okay,
telescopes, because that was also mentioned in the comment.
okay, yeah. My understanding of hydrogen alpha is limited. And again, that's outside the purview of what we're doing.
Okay.
I do know, but again, I do know that they are trying to, that it used to be like, you have a hydrogen alpha filter, oh my God, you know, now it's becoming more and more accessible, and which is great that more and more people can actually buy and use and see the sun at those wavelengths. That's a wonderful, great, positive thing. It's just beyond the purview of what we're doing here.
Okay. All right, thank you. So we did have a couple different questions come in about how can you effectively tell the difference between groups? You know, what's the minimum distance? How do you make that judgment?
That is, I see that Frank typed in just that he has any comments about Mylar and glass filters. So yeah. This is where the experience and monitoring from day to day is important. It's really having these groups be your old friends. It's like, you know, you watch the children in your family are born, you watch them grow, and then members of your family pass on. It's kind of like that with sunspot groups. It's like you watch and see this group of sunspots pop up, and then something pops up sort of near it, and then it's like, okay, that's a different group. And then you can see them evolve separately from each other. So it's a matter of, if you could observe the sun every single day, it would be relatively easy to figure out the different groups, because you would just monitor the you know, their behavior, their evolution. Well, you can't, most of us can't observe every day because either life gets in the way or it's cloudy. Plus, also remember that the sun is rotating. And if you have a group of sunspots that lasts more than 2 weeks, it's going to go behind the sun. And it might pop back around in 2 more weeks, or it might be dead before the sun rotates around. So it's a matter of experience and conscientiousness, and sometimes, to be honest, it's a matter of luck. Mm-hmm. Art, magic, voodoo. We do the best we can, because again, we are not out there with, you know, measuring. If we were there measuring the magnetic field of the sunspot groups, it would be obvious which ones were different groups. But that's not what we're doing. We're comparing apples to apples. We're comparing what Wolf was doing. We're observing in the way Wolf was doing. We are observing the number of spots on the sun and using our best observational skills to figure out where the different areas of activity are and how many spots are in each area of activity.
Thank you. All right. So next question here comes from Michael Gardner, who asks how the K factor for an individual is actually calculated.
There have been several articles that have been published. If you go on, I'm trying to think of where it would be. I believe in the Observer's Guide, it gives you some references of the K factor. The other place is if you go to to JAVSO, to the Journal of the AAVSO, and just do a search for K factor and solar observing, you will see some of the scholarly articles that have been written.
Thank you. Good tip. Next question here. This one comes from Yogesh Chavan, who asks, how often does the sun's magnetic field flip?
It flips about every 11 years.
Okay. Right along.
Sometimes 7, sometimes 17, but you know, yeah.
Okay.
And so you'll hear the sunspot cycle, which is the number of spots. And since the polarity flips and then it flips back, you will sometimes hear of a 22-year solar cycle, which is the flip. Mm-hmm. Whereas the 11 is just the number of sunspots, or one flip. Makes just sense. To make it more confusing.
Okay. So next question here. we have some questions actually about accessories for solar observing. So first, solar finders. Do you have any experience with solar finders that use a pinhole projection of the sun alongside a flat surface on the finder?
I have, short answer is the only solar pinhole finders that I've ever used is in my Sunspotter. If you're familiar with the Sunspotter, it is a really cute, not cheap, folded refractor. It's wood and it's really portable and it's great. It's shaped like a triangle and it's kind of idiot proof. You know, it's safe to use with kids. It's kind of hard to get your head in the light path, which is what I love, using idiot proof sort of things like that. And the way that you line it up with is they have two little pinholes on the front of it. And then they have those, you know, those little white rings that you put on notebook paper to prevent them from being torn by your binder. They have those, and then you line up the sun in those little rings, and then you know the sun is, you're close to being centered. That's the only time that I've ever used a pinhole liner upper. I mean, I know what your viewer is talking about. I personally haven't used those. I just do the look at the shadow on the ground, minimize it sort of thing, and then look and see where I am.
Okay. Thank you. All right. And then the other question we had here about accessories. I guess this is more of a comment. Someone had commented that they use a reticle eyepiece with crosshairs to help them determine the location of the sun's equator because they watch how the sun drifts relative to the reticle. So that's one method. I don't know if you have any comments about that.
If that will help you get east and west and get and yes. But again, remember that the sun's equator is tilted with respect to the earth different ways at different times of the year. That diagram that so just be aware of that.
Okay, thank you. And let's see, next question here. We had a couple come in from Patrick Kavanaugh who asked, first of all, should I use a camera?
Not for what we're talking about here. If you are planning to submit observations to the AAVSO solar section, we would like you to look either with your eyes at the projected image or to look through the filtered image. Again, so we're comparing apples to apples.
Okay. And then a second question here from Patrick Kavanaugh. He was asking about a specific model of filter and whether it's acceptable. I thought that perhaps you could talk about what particular criteria people should be looking for when they are trying to determine if a filter is good or not.
If it is a white light filter, not a hydrogen alpha filter, and it is safe, commercially available, and like again, we know the Thousand Oaks ones because they've been around for years, and other ones that have been around for years. So if it is white light, if it is safe, then that's pretty much what we require.
Okay. Thank you. All right, and then here is a really good question, which just came in from Michael Gardner. How do we join the solar observing section?
Well, every one of the observing sections in the AAVSO has its own forum on the AAVSO website. And so you can join the solar forum and you can chat with solar observers from around the world. And you can begin sending in your observations to the solar section. All you need is an AAVSO observer code, which you can put in a request for through the AAVSO website. And then what will happen is that if you are a new observer, we will monitor your observations and see how you're doing. And we will give you the correct K factor. And if you've proven yourself, you will be folded into the fold and your observations will be in with everybody else's and you'll be one of us. And again, for people, please feel free to ask questions. Like I said, Kim Hay is wonderful. Rodney is great. I try to be good. And Sarah Beck at headquarters is amazing. And so ask any of us, just submit a question through the solar forum, and we will try to get back to you as soon as possible. And please ask questions. Because of the safety issues with solar observing, we really would like people to ask questions, be safe rather than sorry.
Very good advice. Thank you. So I'm pasting into the chat links to the solar section webpage as well as the forum, so that those who are interested in checking out what you do and joining the section can do so. And as Professor Larsen just said, you can join the section by subscribing to the forum. That's how the section system works with AAVSO. Okay. So our next couple of questions here have to do with collaborations. So Gregory Shanos had asked if the AAVSO ever collaborates with the Association of Lunar and Planetary Observers.
Good old ELPO. I have not seen any collaborations during my time being associated. I could be wrong, but I have not personally seen any collaborations with ELPO.
Okay, thank you. And then I saw that Patrick Kavanaugh had asked about if the solar section ever participates in any citizen science projects.
There was I don't know if you would call this a citizen, I would call it a citizen science project, which John Briggs was very much involved in this. And there was an article on the solar section page about this, where they were trying to get people to use a specific type of historic instrument, very small aperture historic instrument, to do solar observing, to see if they could figure out how to figure out the correct K factor for a specific class of historical observations. There was a particular researcher who was interested in this, and so they put a call out for people who had these sorts of instruments to do solar observing and to see what kind of numbers you would get. And again, I believe there was an article about that on the solar section website.
Good to know. Thank you. Okay, next we had a couple of questions about websites and software. So first of all, do you find any use with any software besides Sun Entry in this part of what
Sun Entry is the only one I use, because the great thing about solar observing is it's very low tech. You safely set up your instrumentation, whatever it is, you do your observation. I draw my little logbook picture, write everything down, count, draw my little picture, this, boom, done. No more technology, no software. It's not like doing photometry or CCD work or any of that other, which is great. So the only thing is the Sun Entry, which makes the uploading of information to the database much easier than in the old days, where you had to fill out your paper form and literally mail it in to headquarters. So
that is nice.
Yeah.
And fortunately, you don't need any charts.
Right. No charts needed. We can find the sun, no problem. No comparison stars needed either.
The VSP team will be relieved. Okay. Next question here comes from Gregory Shanos, who asked the website www.solarham.net gives a listing of active regions, sunspot number, and solar flux on a daily basis. Do you ever use this site or find this info to be useful to look up?
There are a number of different websites that take data from various places. Let me back up a little bit. How I first got involved in this was back in the late 80s, when I was still in grad school, and Cap Hosfeld, the former director, a former lead section leader of the solar section. Cap was a real character, and I met him at Stellafane, and he had his little rig up there, his solar observing rig, and I looked through it, and and he was chatting me up, and I said how I just gotten a new telescope, and he goes, oh, you could solar observe. And I'm like, oh, okay, cool. And so he gave me, his contact information. And at the time, he was trying to get observers for the American Radio Relay League, who were doing their own independent solar observing to get their own monitoring of the sun, because ham radio operators, sunspot activity, solar activity affects them. And so I submitted a bunch of things to CAP for the Radio League data. And he goes, your data's good. Have you thought about submitting it to the AAVSO? And I said, what's that? And look at me now. So yeah, start counting spots on the sun, and you too can be the president of the AAVSO one day.
All right, well, I'm very glad that happened. Okay, our next question here, I think this is the last one on websites and software. So this came from Michael on Facebook, who asked, why are the spot counts that I see listed on spaceweather.com more than what I see as an observer?
Part of the issue is whether or not they are counting pores. And again, they are using photographs.
Mm-hmm.
And so you have different resolution. And I have noted that same thing. I know exactly what he's talking about. I noticed the same thing, which is why I did not say, go to spaceweather.com and look at the sunspot number that's listed there. I said, look at the picture and kind of see what the groups are doing and see if something has died in the 3 days where it's been cloudy in your place, right? Or see if something new just sort of sprouted, and it's been, you've been busy and you haven't been able to go out and look. So yes, it's, again, we're trying to compare apples to apples. That is one, that is probably a really good way of showing people why we don't use pictures, why we don't use cameras, why we compare observers who are looking with their eyes, either with a projection or with a filtered image.
Okay, thank you. Okay, next question here. This one comes from Philip Gebhardt, who asks, can amateur astronomers use radio frequencies in order to help determine sunspot activity?
We actually, and let me just get rid of this PowerPoint over here. Hold on.
Okay.
Oh, let me stop. Okay, stop sharing that. Let me go to, hold on. The short answer is that there are ways that you can be involved with the solar section if you are not a person who wants to actually look through a telescope at the sun for whatever reason. We have what's called the SID program, the Sudden Ionic Disturbance. And so what I'm going to do is I'm going to share screen right now and show you this part. It's aavso.org solar.sids. These are observers who monitor very low frequency radio stations for sudden enhancement of their signals. Okay, and so depending upon, again, you're not directly monitoring sunspots, you're looking at the interplay between solar activity, which again is related to sunspots, and the Earth's geomagnetic field, and hence its atmosphere, and the way that radio signals are transmitted through our atmosphere. So if you're interested in doing SIDS monitoring, you can build your own radio telescope. It shows you how to make the equipment, how to build antennas. There are fewer people who do this than do the observing of sunspots, but we do have some dedicated SIDS observers, mostly people who are really into engineering and people who built their own radios back in the day or whatever. So if you are interested, please check this out and get involved. And if I go back to the bulletin, and we can see from the June issue, you can see that we have the SIDS report. And you can see there are a smaller number of people doing SIDS reports, but we have them who are doing their data, and it is valuable because even though we have not been monitoring for as long, we do have a record of this, and so we can compare and see how it has changed over time.
That's very cool. Thank you.
I tried to get students interested in building an antenna, and I paid for the parts, and then the student graduated and wasn't interested. So,
Oh no.
so much for that project.
Well, let's see. So one more question here. This goes back to towards the beginning of your talk when you mentioned that sunspots can be as much as 1,500 degrees Kelvin cooler than the surrounding surface of the sun. That works out to something like the effective temperature of a mid to late K-type star. So does that mean that if you were able to isolate this sunspot and look at its spectrum, would you see those kind of spectral features? Maybe even a little bit of titanium oxide, something like that?
I don't know that anybody's ever asked me that question. The point is that it's cooler, but it's only temporarily cooler.
Mm-hmm.
Again, it's areas that are changing rapidly over the, an astronomical time. I mean, so right. I don't think you're going to get any really chemical changes in the sun there. I mean, it's not a place where, I mean, and if you think about it in the sun, given what the sun is like, the amount of titanium is so tiny in the sun, and then making the titanium oxide, I feel confident in saying the answer is no. It would be really cool if I was wrong, but again, it's a temporary localized cooling, and so it's not going to, do much of. And the fact that we can use the Zeeman effect to measure the strength of the magnetic field there. And it's the normal same Zeeman lines we use for the entire photosphere, the HK lines. So it would be the same. So there really is no spectral difference that I've ever heard of really around a sunspot.
Okay, that does make sense about the very temporal instability going on there. So thank you. Okay, and another question here. This one, are pores physically different from sunspots, or is it just scale that's different?
There are areas that are not intense. The definition of a sunspot that you might commonly see when you look it up is sometimes you'll see magnetic storms on the sun, or areas where the sun's localized magnetic field is 50 times stronger than average. And it's because of that intense enhancement of the magnetic field, because of the magnetic field lines popping out of the sun, that suppresses the convection, that lowers the temperature. Kind of all that sort of has to come together to be a sunspot. A pore is more like a convective cell that might just be a darker area. A cooler area might be a little bigger, so it's more obvious. But it's not really a place where you have this enhanced magnetic activity. Is that making sense?
Yeah, it does. Thank you. Okay, so it looks like we're down to just the last couple of questions. So here's one.
And thank you all for staying past time and being so interested.
It's a very interesting topic.
It is. I kind of like it.
Okay, so let's see. Let's take this one from Yogesh Chavan, who had asked if you could talk about the relationship between solar activity and unusual amounts of it with our observed space weather and disturbances in Earth's atmosphere and stuff like that.
Yeah, it's I kind of rushed through that a little earlier in the talk where, when we have the sun, short answer, we wish we understood the sun's magnetic field better than we do. because it has direct implications to the environment, to what we call space weather. When the sun is incredibly active magnetically, it influences the solar system by sending out enhanced radiation and high energy particles and magnetic field lines, and they interact with other bodies that have magnetic fields like the Earth. So what we really are interested in is those interactions between the sun's magnetic field and the Earth's magnetic field and the Earth's atmosphere. Unless you have specialized equipment, including satellites observing the sun, it's kind of easy to miss solar flares or coronal mass ejections. But you can't miss a big group of sunspots. Now, there's not a one-to-one correspondence between big group of sunspots and coronal mass ejection, but the Venn diagram has a big overlap.
Mm-hmm.
So by monitoring solar sunspot activity is a very easy way to kind of know when you should be concerned about a higher likelihood of solar activity. Like, let's say, like I said, nowadays we have all these satellites and all this other stuff. Let's say that worst case scenario, we lost all of our satellites. We had no solar observatories. The only thing we could do would be to look at sunspots. Oh, kind of like what they did in the 1800s, you mean? Yes. We could still make a rough prediction of when it would be more likely to have geomagnetic storms just by monitoring sunspot activity.
Makes sense. Okay, thank you. All right. So next question here comes from Patrick Kavanaugh, who asked, during a solar windstorm, are there sections that are positively charged and sections that are negatively charged? Is it segregated like that?
He's getting beyond my comfort level of specialization. Basically, what happens in these solar storms is that you get charged particles streaming out of the sun. What are these particles? Well, they are mostly protons. Protons are positively charged. Alpha particles, which are helium nuclei, they are positively charged. But you also have electrons, which are negatively charged. And when these positive and negative particles interact with a magnetic field, because of their different electric charge, they will move differently in the magnetic field. So there is a separation, if you will, of charges, just because the particles, some are positive and some are negative, and the way that positive and negative particles, like if you use the right-hand rule in physics, the direction that the particles will go in, there's a relationship between charge and direction. So the short answer is, yeah, there's something going on. Yes, but it's kind of more complicated. But I've given you sort of the simple answer there.
Okay, thank you. And just one more question here. This one goes back to the plot that you had shown of the sunspot count for the northern hemisphere versus the southern hemisphere. Do you know why they reach their maximum apparently at different times?
That's one of the things we're trying to figure out. Again, there are lots of things about the sun's magnetic field that we don't completely understand. Mm-hmm. And there are hypotheses about all this, but the point here is that we're working on it. That would be the answer I would give in confidence, is that because if you think about it, if we are in sunspot cycle 25 right now, okay, think about a data set where you've only got 24 previous points. You come up with a theory based on 24 data points and see how accurate it is, right? Mm-hmm. So if we've only seen 24 solar maxima that we have confidently measured using modern technology, that's a limited data set. And each maximum is different The amplitude is different, and the time between the two maxima is different. So it's a pattern, but it's not a perfect pattern. So we have a limited data set, and it's a data set of some sort of process that is not perfectly regular.
That sounds like
good luck with that one. Good luck with that one. I remember Magic 8-Ball.
Mm-hmm. That sounds like the best case I've heard yet for starting solar observing. So yeah. Everyone out there, if you can, this needs studying.
Yep, it does.
Okay, and I think that that's it for our questions. So let me go ahead and put up our closing slide. As soon as I get my meeting controls back, wherever they went. There we go. All right. So I would like to begin with the most important of closing announcements, and that is I would like to extend a heartfelt thank you to Professor Larsen for sharing your time and knowledge with us today and giving such an excellent presentation and Q&A. Thank you. This was wonderful. I would also like to thank again our sponsors, Boyce Astro and Chroma Technology. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving both the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation, surgical devices, machine vision, multispectral imaging, and of course, our favorite, astronomy.